Okay, so I'm just gonna go over a little confidence interval theory. Okay, we got a pen. Confidence interval theory. So if we're asked to make some kind of estimate for a population parameter, and so a population is some big group, like maybe all people in the United States, or everybody in Oregon, or everybody in a certain town, or maybe all cows that make milk, like from that last week. A parameter is some measurable characteristic in the population, like the percent of people who believe something, or the average value of something we can measure. So there's, at this point in time, we can make two types of confidence intervals. We can either make a confidence interval for a mean, or we can make a confidence interval for a proportion. So I'm going to combine the review with Dakota's question here. If it's a mean, we kind of have two options on how to make a confidence interval for a mean. There are other options, but we only have two. Either we know the population standard deviation, that's what we call sigma, or we don't know it. Okay, so, and then think about it, if we're asked to estimate what the mean is, how on earth are we gonna know the population standard deviation? That's like a harder thing to know. So typically you're usually down this branch. So maybe I'll highlight this branch because this is actually where you go more often. See, I don't like red, let's do yellow. So in reality, this is kind of where we should end up in statistics, but sometimes we do end up here. But my belief is we kind of end up here in the beginning of stats courses because it's easier to consider and we're trying to learn this stuff. If we know the population mean, then we can calculate what we call the error bound on the mean by taking what's called a z-score, and a z-score is related to a normal distribution, and we multiply that by sigma, and then we divide by the square root of the sample size. And this tells us what the error on the sample mean is in terms of estimating the population mean. That z-score right there comes from a normal distribution, and it's related to the confidence level. So if you think like picture-wise, drawing a little sketch of a distribution, and most of these distributions end up being bell-shaped in terms of for the mean or the proportion, but maybe not for individuals. So in the middle here is our x bar, or like z equals 0, like we haven't strayed from the middle. And remember, a z-score is just a measure of standard deviations, so no deviation. And then somebody gives us a confidence level, and the confidence level is like 95% or 90% or whatever. So that's the percent we put in the middle. And then there's these tail probabilities. So the tail comes from taking 1 minus the confidence level, right? So that could be like 1 minus 0.95. And that would put 5% in the tails, but the tails have to share that, so they get half of that. And this calculation here is called alpha. So 1 minus the confidence level is called alpha. That's sometimes referred to as the significance level, and we have to split that in half. So alpha goes in each tail. The z-score I'm referring to is the number of standard deviations I need so I can put alpha over 2 in the tail. So like for this example, if this was a 95% confidence level, that would put 2.5% in the tail. And so the question is, what z-score goes with 2.5% to the left, okay? And that's also called a percentile. So to find that z-score, we would have to use a normal distribution. Okay, so this is, again, I'm doing a kind of overview of the theory here with some formulas, and we'll apply it in a sec. So to calculate that z-score, I need something like StatKey or a spreadsheet calculator, or a scientific, like a TI calculator can do this, a Casio calculator, graphing calculator can do this. On the, let's see, let me get the wording right. I like the spreadsheet, and I believe the formula is called norm.inv for inverse, because usually we know this number and we plug it in and it gives us the probability. We're going backwards. We know the probability, we need the number that leads us there. And so I would enter whatever alpha over 2 is as a decimal, And then it wants to know what's the mean. So in this case, the mean would be x bar, and it would want to know what the standard deviation is, and that would be this sigma over square root of n. And I think that's the end of this calculation. Let me whip out my spreadsheet to double check. And all these smartphones that spell check us and spreadsheets that tell us the meaning of everything kind of keep us from memorizing stuff. So I'm just gonna, let's see, bring up a new tab. And if I start typing equals norm, yeah, I want the norm dot inverse is the better one to use. And it says, what's your percentage? What's your mean? What's your standard deviation? Yep, okay, so that's what we want. I had it right. So that's how we would find that z-score right there. And then we should have been given sigma, the population standard deviation, and we should have been given a sample size. And based on that, I can calculate the margin of error. All right, so if I don't know sigma, let's do that one in green. This one happens more often. Then to find the error bound on the mean, instead of a z-score, we use what's called a t-distribution. And it's kind of like a normal. It is bell-shaped, it is symmetric, it's just a little wider than a typical normal distribution. And we don't know sigma, so the best substitute for the population standard deviation is the sample standard deviation. And then, like before, we divide by the square root of n. So these formulas are pretty similar. A z-score and a t-score are similar, but not exactly the same. And S, the sample standard deviation, is our best estimate if we don't know the population standard deviation. And again, this is the sample size. The t-score that we need here is calculated a little bit differently than the norm inverse. We need a formula called the t inverse, so that's t dot inv. And the spreadsheet capitalizes these, but it turns out it's not case sensitive. And then what it wants to know is, let me get this right, it wants to know alpha over 2 again, and then it wants to know what's the sample size minus 1. And that particular value, the sample size minus 1, is also called degrees of freedom. And the history of that phrase is a whole nother topic, so I'm not going to worry about that. So I would have to calculate this on a spreadsheet or a calculator, or Stackey will just whip this out for me without a formula, which is kind of nice. And so I'll demonstrate that in a moment. So that's how I would calculate the error bound there. And then for a proportion, let's switch to back to blue maybe. For a proportion, we would need to know, let's see, some sample information like what's the sample size and what is the sample proportion. And then there's this other value that we can calculate, which is called Q prime, and that's always 1 minus P prime. So P prime is the proportion of successes, and Q would be the failures. So if we're working on a proportion, then we're going to calculate the error bound on a proportion, and that's going to be kind of like the first one here. It uses a z-score, so we'd have to find the appropriate z-score, and then we multiply that by this crazy square root, where we take p prime times q prime and divide by the sample size. And all of that p prime, q prime sample size has to go inside the square root there. To find the z-score, it's similar if you're using a spreadsheet. So that z-score is, again, a norm inverse. And in the norm inverse, we would tell it, let's see, our alpha over 2, just like the other ones. And then the mean for proportion is the proportion. So then it would be p prime. And then we would enter this square root for the standard deviation. So I'm gonna have to write that underneath. And so on a spreadsheet, let's actually do that. It would be SQRT is how you tell a spreadsheet to do a square root, parentheses, and then give it P prime times Q prime divided by N, and then close the parentheses for the norm dist. Now, in this situation, so those are the formulas you need if you happen to make a confidence interval. So if you're making a confidence interval, you have to decide first, are you a mean or a proportion? Okay, if you're a mean, do you know the population standard deviation or not. And then these are the formulas if you don't, and these are the formulas if you do for a confidence interval. If it's a proportion, then you need to make sure you have the sample size and the proportions from the sample, and then based on that, you can calculate the margin of error, which is what this formula is for. And instead of using the norm inverse and the t inverse here, I could use stat key instead. The downside of stat key is it doesn't give me as many decimal places. If we only need like 3 decimal places, stat key works fine. But anytime we need more than that for more sensitive tests, then we would have to use a spreadsheet or some other calculator. Okay, new page. Now let's do a screenshot of that problem and get it done. That's not the problem, that's the problem. And screenshot. And it says to give whole number of people. So add to new page, please. Okay, so a political candidate is asked to conduct a poll to determine the percentage of people who support her. Okay, so this is a proportion, so right away I want to determine the percentage of people. So determining some percentage means I'm doing a confidence interval and it's for a proportion in this case. So I'm just going to make a note of that. This sentence means find a confidence interval for a proportion. So on my previous page of notes, I'm in this region over here. So I'm gonna have to apply this formula in a moment. Okay, the candidate only wants a 2% margin of error. Oh, so the candidate's saying, hey, you can't have a margin of error that's bigger than 2, right? I want a 2% margin of error. Okay, so good to know. So they're saying, hey, the error bound on the proportion has to be 2%. And usually we write that as a decimal. So I'm gonna put it as 0.02 with a confidence level of 90%. So we'll apply that in a second. So we have a formula for the error bound, and that says that you need to find the right z-score, and the z-score depends on the confidence level. And then you multiply that by the square root of the whatever p prime is, whatever q prime is, and then divide by the sample size. Now, in this case, the candidate wants the 2% margin of error, and we have to figure out what sample size gets us that. So that n right there is what we don't know. Oops, what happened there? That was weird. So we have to find it. Now, also up here, we don't actually know what the sample proportion is. So we have to guess, and the rule is if you don't have a previous thing to go on, like, oh, we thought it was like 40%, or we thought it was 80%, then you just say, okay, let's let it be 50%. Okay. So just a note, if no previous information exists, then we let p prime be 50%. Because q is always 1 minus that, so q has to be the same. So we're in the middle, we don't know. 50% like her, 50% don't, that's the default. And so that's the safest thing to go for. Q, remember, is always 1 minus p, 1 minus 0.5 is 0.5. So filling in what we know, so again, this formula is equal to the margin of error, and she said the margin of error needs to be 0.02. And we got to figure out how many people will get us to that margin of error. So let's see, what do we know so far? We still don't have z, but we have p prime and q prime. So I'm going to fill in what we know. Z is still not sure. And then I've got p prime is 0.5 times q prime is 0.5. And then n is definitely unknown until we solve this whole mess. Okay, at the moment, though, we have 2 missing variables. So we need to figure out what z is. And z always comes from the confidence level. And so I mentioned back here, to find the z-score, you got to use that norm inverse or whip out stat key. So I'll do both right now. So let's go to my spreadsheet. And let's see, let's label this. This is practice 12. And then up here, let's label some things. We're trying to estimate sample size for proportion. And what do we know? We know we want the error bound on the proportion to be 2%, so 0.02 as a decimal. We know the confidence level is, what was it, 90% that she said? Double check. Yep. And since we don't have anything else to go on, we're going to have to assume that P prime is 50%. And if I type the percent, that's like 0.5, but making it a percentage, or you could just type 0.5, either way is fine. And then Q prime is always 1 minus P prime. So I'm just going to actually put in a Q prime here too for fun. And it equals 1 minus the number above. All right, so this is the setup information there. Next thing I need to do is find the z-score that goes with this confidence level there. So I'm also going to figure out, and let's actually add a few new lines here. Shift this down a touch. So there's the confidence level. Alpha, I mentioned earlier, is always equal to 1 minus the confidence level. And then we have to split that to the tails, so we also need alpha over 2. So that would be just equal that alpha divided by 2. So I need to put 5% in the tails. To find the z-score that goes with that up there, and I guess I could put that, I'll just leave it here. So z, that I mentioned is the norm dot inverse. So that would be this one here. And it says, what's your tail probability? So it just calls it the input of the inverse normal function, right? So I wish a human wrote a better description of that. So they should say it's the tail percentage, tail probability. That's my alpha over 2 up here, comma. What's the mean? Okay, now here's the catch. Normally with a proportion, we say the mean, oh shit, I screwed that up. The mean is the proportion, but if I'm talking about a z-score, z-scores count standard deviation, so the mean of z-scores is always 0, the mean is in the middle, and 1. So I gotta fix those notes, I screwed that up. So this says the z-score is gonna be negative 1.64, and we'll ignore that negative. So let me fix my notebook. Okay, what did I calculate here instead? Oh, this actually calculates the lower limit. Oops. Too many formulas. So bigger eraser. That is incorrect. Should have just put a line through it. Oh well. So the z-score, it is the norm dot inverse. And we do need to give it alpha over 2, but since we're finding a z-score comes from what's called the standard normal distribution, and the mean is always 0 and the standard deviation is always 1. The other version of the formula actually would have calculated the lower bound of my confidence interval, so I could double check that in a minute. I think I have the same problem here. Yep. This would actually calculate the lower value of the confidence interval. So I don't want that or that. I want a 0 and a 1 there because I'm looking for a z-score. Z-scores always have a mean of 0 and a standard deviation of 1. All right, back here. So I just found that z-score, and I'm just going to go with, let's see how, they wanted to the nearest whole person, so I could probably round to 2 or 3 decimal places. So I'm going to call it 1.64. I think 2 decimal places might be okay. If you're a little gun shy of too few decimal places, we could call it 1.645. Maybe I'll do that for fun. Okay, so I think the z-score here, what color am I in? I want blue, would be 1.645 times this. And I can clean this up a little bit, right? 0.5 times 0.5, that'd be 0.25. And the reason I can't do that over n. And so what I have to do is once I get all those values in there, I have to then solve this for n. So to solve this, solving equations, you unwrap it from the outside. I first have to get rid of the 1.645. So I'm going to divide 1.645 to the other side. And there's no need to calculate this yet. We'll just wait a moment on that. So this divides out. A number divided by itself is 1. 1 times anything is that thing. So what I'm left with here is that 0.25 over n is inside the square root, and it's equal to whatever that fraction is. And I don't care what it is yet. I'm just going to leave it like that. To get rid of a square root, I then square both sides. So that gets rid of the square root. So now I have 0.25 over n is equal to whatever that sucker is squared. And then the last step would be, there's a couple ways to solve this from here. We could kind of cross multiply and divide. And so I'm just going to jump to the end here. If I do that, then what I'm going to get is, let's say n equals, this thing gets flipped when I cross multiply and divide. So that's going to be 1.645 over the 0.02. All of that's still squared. And then this is going to stay where it is. 0.25 is going to stay there. So that calculation will give me the number I want. And if you look in the book solves this for you and gives you a general formula to plug in, and I'll write that down in a second. But sometimes it's fun to do algebra. I haven't done any in ages. Let's see, calculator. So I have all of this in my spreadsheet, so I can just use it. So my estimate of n is going to come from that. So it's going to be equal to the 0.25, which was the p prime times the q prime, times parentheses, the, let's see, was the z-score on top? Forgot now. The z-score was on top, yep. Times the z-score divided by the presumed margin of error. Oops, oh no, stop it. Which was the 2% up here. And then that parentheses needs to be squared. Okay, so this says if we really want to give this candidate a margin of error of 2%, then we need to, you always round up to, so I would need to survey 1,691 people. Okay, so hopefully this candidate has a good amount of money to spend because it's going to take a little time and energy to survey that many people in a random sample, right? It's got to be a random sample too. We can't just go to one big apartment building and survey everybody there for convenience. So that's the estimate on the sample size for my version of this. So the general formula for that, new page, is given in the book. So again, this is a proportion, confidence interval, sample size. Got a couple other requests there. Yep, I'll get to those in a moment. And the sample size is going to be equal to p prime times q prime times the z-score squared divided by what you want the margin of error to be. So we call it the error bound on the proportion, and that's got to be squared too. So I wrote it a little bit different than when I solved that equation, but let's just double check that that compares to what I solved back there. So the p prime times the q prime, that's where the 0.25 came from, right? 0.5 times 0.5 is 0.25. That z-score, it was the 1.645, that ended up in the top and it was squared, and the margin of error the candidate wanted ended up in the bottom and it was squared. And so you can see I have all those components just written a little bit different. So you could just jump right to this formula if you need to know the sample size for a proportion. There's a similar formula for a sample size for a mean for a confidence interval. Yes, I will have this this video posted later, and I'll probably split it up into a few smaller videos. Good luck. Okay, so sample size for a mean, if we reverse the formula I wrote in the flow chart over here, that the error bound is equal to this right here, we have to solve for n. So let's see, I have to write that down and get it right. Oops, wrong button. Okay, so the original formula was that the margin of error, the error bound on the mean, was equal to the z-score times sigma divided by the square root of n. Okay, so when I solve that, I'm going to get n equals, goes up, those stay, we're going to get z times sigma divided by the margin of error. And then to get rid of the square root, we got to square all of it. So that would be for a mean if I know sigma. If I don't know sigma, then that means I would have to know t. So this is for, let's make a red note. Sigma is known, which is unlikely. Usually sigma is not known. Then the sample size there looks almost like that, but we replace the z with a t, and we replace the sigma with the sample standard deviation s. And these formulas are in chapter 8. So this is all chapter 8 stuff in the book. Okay, hopefully I answered that adequately. I am going to split the video now.